Okay.
Hello, everyone. Today we have Nart Shalqini from Virginia Tech, and we'll be talking about optimal tilings of the unit square. Before we begin, let us recall our guidelines. We are all learning, everyone has something to contribute, and no one has all the answers. With that, Nart, take it away.
Oh yeah, that was very relieving to hear. This is my undergraduate research project, and since then I've been doing coding theory. So I might be a little rusty on the topic. Hope I can recall everything correctly. But it's a really fun topic that I enjoyed doing as an undergrad. So hopefully you guys like it as well. And just don't hesitate to interrupt if any questions you have during the presentation. All right, so let's begin. Um, so, so I'm gonna define what the tiling of a unit square is. So we suppose that we have a unit square, which is a square with edge length 1, a packing of a unit square with n smaller squares, such that their interior is disjoint, and their area adds up to 1 is called a tiling. And in this case, we denote a particular tiling with n small squares as T of n. So here, for a given n, you might have different looking tilings. So here I have two different configurations for T of 8. The one on the left appears to be slightly more symmetric. The one on the right has 3 different tile sizes. However, this one over here, although it's a packing, it's not really a tiling because the smaller squares do not entirely cover the big square. And I think of this corner, top right corner here as like being empty, not tiled by any square. So although Erdos considered packings in general, I'll also only be thinking about tilings today. So it's not immediately straightforward if we can tile a given square with n smaller squares. But it turns out that this is true for n greater than 6. And it's obvious, I suppose, after a little thinking that you cannot do this with 2, 3, or 5 tiles. So the proof is basically an induction proof. So if you want to cover the case when n is divisible by 3, you start with a tiling of 6 squares. And in this case, I chose this particular one. And then you just subdivide one of the squares into 4 squares, in which case you will be removing the bigger squares and adding 4 small squares. So you'll be adding 3 squares in total. So if you start by 6 and keep adding 3s, you'll have all multiples of 3 covered. And then for the case when n has remainder 1, you start with a tiling of 4 squares, and you repeat the same process with subdividing a square into 4 smallest square, in each step adding 3 tiles. And finally, for the case when n has remainder 2, you start with 8 tiles and you repeat the same process. And then this covers all possible values of n greater than 6. So yeah, this is just a regular strong induction proof. And then, so the quantity that we are interested in here is the sum of the side lengths of each smaller square. So given a tiling T of n, I consider the sum of the side lengths of each smaller square. So I take the side length of each square and I sum them up. So here the sum goes from 1 to n of Si, where Si represents an edge. So it turns out that this value can be different for the same number of tilings depending on our tiling configuration. And so if I look at the previous examples I had with 8 square, an 8 square tiling, the one on the left is going to have a slightly bigger sum of side lengths of the edges than the one on the right. And you can calculate this directly. The big square has side length 3/5. The medium squares have side length 2/5, and the small squares have side lengths 1/5. And if you add them all up, you get 2.6. You get the same thing for the square on the right-hand side. So Erdos and Soifer asked the value of the following question. So we were interested in, so given n, so if I consider all tilings of a unit square with n smaller squares, what is the maximum possible sum of the side lengths that I can obtain? So in this case, since I'm considering tilings with 8 squares, I know that f of 8 is going to be at least 2.6 because of my particular example on the left. But I'm not sure I don't know if I can obtain a value greater than 2.6. And it turns out that this problem is pretty difficult. And we have used ad hoc methods to calculate this for specific values of n. And we proved that indeed when there are 8 tiles, this is the optimal tiling. So the tiling on the left is the optimal one. And then there doesn't also appear to be a nice pattern between numbers. So we decided to investigate this more, maybe focus on specific values of n. So in order to make this, so we first began by trying to look at the patterns of tiles with n squares. So we had to write software programs for those. And in order to make the problem more computationally tractable, both in order to use some number theory and in order to be able to program some software, my advisor and his collaborator introduced the minimal tiling property, which I'll refer to as MTP moving forward. And then we see that tiling T of a unit square has the minimal tiling property if every tile in T can be tiled by the smallest tile. So we thus have the hopefully easier problem of determining f of n. So in this case on the left, I have an MTP tiling because if I look at the small squares, then each of the small square can tile the other intermediary squares, right? So the medium square can be tiled with 4 of the smallest square, and the biggest square here can be tiled with 5 of the smallest square, and of course the entire unit square can be tiled with 8 times 64 of the smallest square. Sorry, 25 of the smallest squares. And then the one on the left is not an MTP tiling because the smallest square cannot tile the medium square here, right? So we wouldn't consider this. We would only consider like something like on the left. So yeah, so of course we also have to check that MTP tiling exists for all n. So given any number n, we can have a tiling that's MTP. And then this is easy to construct if n is even. So if n has the form 2k, we consider the small square of a size 1 over k, and then we have a row of k squares, and then we have k minus 1 squares vertically, and a 1 square in the middle, one big square in the middle, and this will give me a tiling of 2k squares, and of course the big square can be tiled by any of the small squares. And if I want to make this odd, I do what I did previously. I just subdivide one of my small squares further into a 2x2 grid. So in this case, I'll get 2k plus 3, a tiling for 2k plus 3. And Any questions so far? Just checking if everything is clear.
Just a question, maybe a dumb
Yeah.
one. But why are we interested in the maximum and not in the minimum, for example? Is it trivial what the answer of the minimum is?
I think actually, I think my advisor showed. I don't think it's trivial. The minimum is not trivial either, but I think he did show trivial tilings that obtain the minimum for certain classes of n. So it's easier to show it for the minimum, but not trivial, I would say.
Okay, thank you.
Yeah, yeah. Okay. So the next step is to try to bound the side length of the smallest tile either below or above. Because we wanna use some sort of a software program, so we have a finite set of choices, right? Where to begin. Since when we have MTP tilings, we only care about the smallest tile now, more or less. So the following bound works well for smaller values of n. So any tile size of an MTP tiling is going to have a length at least 1/2 to the n. So n is here the number of tiles. So this shows that if I have an MTP tiling, the smallest tile cannot be too small, and of course it cannot be too big because it cannot exceed 1. So this certainly reduces the number of possible tiles to a finite setting. But the proof turns out to be non-trivial. And so today I'm going to focus on the proof for how we obtain this lower bound. And then I'm going to also talk about how we improved this lower bound for certain classes of n. So before I proceed to the proof, I want to talk a little bit about electrical network theory. Some of you might be familiar with this, but some of you might not. So I've tried to simplify this as much as I could without losing the crux of the story. So basically, I suppose I have a graph with a vertex set V and edge set E. And now I think of the G as an electrical network. So I pick two distinct vertices A and B, and I connect them to some external power source. In this case, you can think of it as a battery, and this introduces electric current to the graph. And then I can ignore this power source, and I can think of edges as wires through which the current flows, and I can think of vertices as junctions where wires are connected to each other. And I also suppose that each edge has positive electrical resistance, R of E. And then we have like this famous result from physics, which says that for any circuit or any wire that has ends V and W, the current that flows through E from V to W is directly proportional to the difference in electric potential within the ends. So if I want to see the total current that flows through each edge or part of a circuit or the entire circuit, I just have to calculate the difference in potential of the endpoints. And I also have a Kirchhoff's current law, which says that the total amount of current that flows into a vertex equals the total amount of current that flows out of it. So this part is mostly physics so far, but it turns out that if we use Kirchhoff's and Ohm's laws on certain graphs, then they can also reveal combinatorial insights about the structure of a graph. So I'm gonna make some simplifications here before proceeding to a proof. First, I'm gonna assume that each edge has unit resistance. Second, I'm going to assume that there are W units of current that flow into vertex A, go through the network, and leave through vertex B. And in addition, I'm going to assume that vertex B has 0 electric potential, so it's grounded. And I'm going to let P be the vector which represents the electric potential at each vertex I. So Pi means that vertex I has potential P. And now this is the math part. So if I let L be the Laplacian of G, then by combining Ohm's and Kirchhoff's law, I can obtain the following identity. L of P equals W times the first unit vector minus the nth unit vector. So the equality itself follows from Ohm's law, since the right-hand side represents the total current that flows in and flows out, and the left-hand side represents somehow the sum of individual changes in potential at each edge. So this is where the identity follows, and Kirchhoff's law follows, and then the right-hand side, the total amount of current that flows in and flows out must be the same. And we know that we have W units of current that flows out through the first vertex, and W unit of current that flows out of the last vertex. And in this case, I have denoted my first vertex with P1 and my last vertex with P of M. So P1 is A here, and P of M is B. And this is how I obtain my identity. So I'm gonna use this interpretation of Ohm's and Kirchhoff's law to obtain the lower bound that I mentioned before. So I'm gonna briefly go through the sketch of a proof. So the claim is that any tile size of an MTP tiling has length at least 2 to the negative n. So the proof, so we first need to translate a tiling into a graph. And in this case, in order to make it more visually clear, I have assumed a rectangle instead of a square. So, but in the end of a proof, I'll make an assumption that requires this to be a square instead of a rectangle. So what I do basically is that I consider each horizontal connected component of the tiling. So in this case, I'll have 5 connected components. So this is the one on the top, and then this is the 5th is the one on the bottom. And then I have 2 that are in the middle. Some of them only share 2 squares. Some of them might share more than 2 squares. So, and then I map each of these horizontal component to a vertex. So I'm mapping edges to vertices in this case. And then I map tiles to edges. So this is a little confusing. You would normally expect to map tiles to vertices, but in this case, I'm mapping tiles to edges. And not if a tile is bordered by 2 horizontal components, then it will be connected to the respective vertices. So in this case, there are 2 edges between 1 and 2 because the horizontal component 1 has 2 smaller squares below it on the right-hand side that also connect to the horizontal component 2. So I'm gonna stop again and see if people have questions about how this construction works. Yeah. So now I'm gonna also place my tile on XY coordinate, and I'm gonna place the bottom of the edge rectangle at the coordinate y equals 0. And I'm gonna let Q of I denote the y coordinate of a horizontal boundary that corresponds to vertex I. And then I define a vector Qi up to Qm. So in this case, Q of m is going to be 0, which is Q of 5. And Q of 1 is going to be h, which is the length of the height of my rectangle. And then my vector is going to be 4, 4, 3, 2, 2, 0. Because so I have 2 2s, I have 1 3, I have 1 4, and I have 1 0 here. And then now I define the electric potential at vertex I to be Qi. So the height of a horizontal component. And if there's an edge that connects vertices I and j, I say that there is a current of Qi minus Qj units flowing from I to j. I assume as previously that each S has unit resistance. And I let W be my previous W. So the total unit of current that flows through vertex 1 and leaves out of vertex 5. And in this case, W is going to be the number of smallest tiles I need to cover the horizontal boundary. So if I rescale my square, so that the smallest tile has edge length 1, then my rectangle is going to have width 9, because I'll be able to cover the width with 9 little tiles. Okay, so I'm gonna see if this is clear to people again. Okay. So now, if you think a little about it, by the way we constructed this, it follows that this circuit does satisfy Ohm's and Kirchhoff's laws. And our goal is to show that W is less than 2 to the n, because we rescaled the smallest tile to have edge length 1. So by Ohm's and Kirchhoff's law, I have that L of Q will equal W of E1 minus W of En. And if I just divide out by W, I can reframe this as equation of L of P equals E1 minus En. So I basically want to solve a matrix equation. I want to solve a system of linear equations. So in the previous example, in the example of my tile here, in a rectangle, this is going to be my Laplacian matrix. So we want the unique solution with the last component being 0, and that's because we assume that the last component has 0 potential. But this is equivalent to solving L prime P prime equals E1, where L prime is the Laplacian matrix without its last row and column. And P prime is just the first m minus 1 components of P. So in our example, I would have L prime. If I truncate this matrix, so I remove a last row and column, and the P that I obtain after solving L prime P prime equals E1 is 1/843,220. Note now that L prime is always going to be invertible, so this will always have a solution, a unique solution, with the last component being 0. So now we proceed to the proof. So we let D be the determinant of the truncated matrix, L prime. Then we know that dP is a vector of integers that is a scalar multiple of Q. Since the entries of Q are relatively prime, and the fact that they are relatively prime comes from the MTP assumption, because the smallest square has to tile all the other squares. there must be the vector must the GCD of all the components of Q must be 1. So since the entries of Q are relatively prime, in fact, dp is an integer multiple of Q. So dp1 is an integer multiple of Q1. And now we use the fact that I'm only dealing with squares. So my height equals my width. And since P1 equals Q1 over W, and Q1 is the height and W is the h, then I know P1 equals 1. And since Q1 equals W and dP1 is greater than Q1, this shows me that D is greater than W. So my determinant is always going to be greater than my width, the width of my square. And now we use a matrix tree theorem. We know that the determinant is the number of the spanning trees of a graph G. And then we know that there are at most 2 to the n spanning trees, where n is the number of edges of G. But the number of edges of G is the number of tiles. So I essentially have proved my claim that my width cannot be too big, given n tiles. So I'm gonna stop again to see if people have questions about the details of a proof. Might be a little dense. Okay. So now we proved. So now this is good because we actually made the problem computationally tractable. We can now have a finite number of cases for a given n, but the bound is pretty crude and not useful for computational purposes unless n is small. So we also try to work on better bounds. And I managed to, in fact, improve a bound quite significantly if n is k squared plus 3. Then the smallest tile of an optimal tiling has to have length at least 3 to the k cubed. So this means that if I want to find optimal tilings for this value of n, I only have to deal with the cases when the smallest tile has length at least 1 over 3 k cubed. And the idea behind this is that I divide the unit square into a k by k grid, and then I divide the square further into a 2 by 2 grid. Then I obtain a tiling with k squared plus 3 tiles. And if I sum the side lengths for an arbitrary k, they will be k plus 1 over k. So here I have an example of 3 squared plus 3. So I have an example of tiling with 12 squares. And the sum of the side lengths here is going to be greater than 3 plus 1/3. So now if I want to look at optimal tilings, I have to make the assumption that f of n is greater than k plus 1 over k. And then using this fact, we can improve a lower bound, it turns out, exponentially. So this is good. And in fact, the proof for this was much easier than the proof using electrical networks. You use some linear algebra and Cauchy-Schwarz inequality relating the area of a square, which is 1, to the number of tiles and the sum of the side lengths. And you use the fact that f of n is greater than k plus 1 over k. So again, we have certain conjectures. So we conjectured that f of k squared plus 3 equals k plus 1 over k. And f of k squared minus 3 equals k minus 1 over k. So in particular, we conjectured that when n has a very specific form, it obtains the optimal values. So if n is k squared plus 3, then you consider a k by k grid and subdivide one of the smaller squares into a 2 by 2 grid. And if you want to consider k squared minus 3, you simply take out a 2x2 grid. And we say that these specific configurations also obtain the optimal value, which we conjecture to be these values above. So we move next to, so we tried to work on this a little. So after some point, we were only dealing with these two cases because we couldn't really find we couldn't conjecture a formula for other forms of n. But we did manage to prove these cases in certain instances. So if n is k squared plus 3, then f of n is going to be k plus 1 over k if we consider tilings without a unique minimal tile. So my advisor and I proved this for the case when there are 3 more squares than a perfect square. And I also, basically by imitating his proof, proved that if n is k squared minus 3, and this should be minus here, when f of n is k minus 1 over k, but only we consider tilings without a unique minimal tile. So there are a few remarks. So the proof's heavily dependent on the fact that the tilings are MTP, and there doesn't seem a way to generalize this when tilings are not MTP. So MTP is a pretty strong restriction. And also the proofs very much depend on the form that n has. So they very much depend on the fact that n is 3 more or 3 less than a perfect square. And answering the original question of Erdos, we thought the MTP assumption appears to be very hard. So yeah, my advisor is still working, but he's so far managed to only prove optimal values for specific values of n. And of course, the open question that remains right now is to cover the case when there is a unique minimal tile and the tiling is MTP. So we still want to know whether this upper bound works if the MTP tilings, without the assumption that there is a unique minimal tile. So I'll stop again to see if people have any questions about this as well.
By the unique minimal tile, you mean there are 2 tiles of the same size, right?
Yes. Yeah. So
Minimal.
without the unique minimal tile, I mean, yeah, there is at least one other tile of the same size. Yeah, like, let's see if I have an example here. So yeah, here, for example, this has 4 tiles, 4 smallest tile. It doesn't have a unique minimal tile. Yeah. 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 So, and it seems like for that case, you need to encapsulate some additional geometric intuition that maybe we haven't done so far. Yeah, because this proof mostly relied on number theory, not really anything intrinsically geometric. So maybe there's something there that you need to look into. Yeah. But yeah, that was for today. I think it's a little shorter than I intended to. Yeah.
Oh, okay. Let's thank Nart for this amazing talk.
Yeah. Any questions?
Yeah, the floor is now open for questions. I do have a question about the previous. So, how
Yeah.
exactly does one figure out the electric network interpretation? in the
So
first place?
this interpretation was already done before by like in 1930s in a different setting by Tutts and some other Brooks and other people. My advisor, so they use this to prove some other property of tilings or packings. So my advisor looked into that and basically some sort of made an analogous proof for the case when the tilings are MTP. But yeah, it seems quite out of blue to relate it to electrical networks, but those people were pretty smart, you know, Tuts, right? So yeah. Yeah, it's kind of hard to wrap my head around how we would come up with relating it to circuits, but we did.
And the proof allows you to do stuff for rectangular shapes. Have you looked at something like given an aspect ratio like the side of the rectangle is 2 times this other side? What about those cases for smaller?
What do you mean, like for other shapes or?
Yeah, for like rectangles, have you considered for smaller n?
This also, I mean, they use the electrical networks also in equidissections, so they also use it when you have triangulation, I think, or other polygons. Yeah.
But this
So
doesn't give you the
it's
optimal, right?
no. It's
Yeah,
used to provide bounds.
So maybe like
Yeah,
for
but
4 square tiles, if there's like a good covering of some rectangle in that way.
So you're asking if you can use this to get optimal values for specific values of n?
Yeah, for like covering a rectangle. Or for example, if you want to cover a rectangle with side 2 and side 1, then there is a way to do that with 2 squares. Which might
Yes.
be like the optimal tiling. But
Oh yeah.
for example,
yeah.
Like if your starting shape is a rectangle and you want to tile it, have you?
No, we haven't looked into that. Yeah. There is like this the guy from Yale. So there is I forgot his name right now. A person in Yale that also used to work on optimal packings, and he published a paper on tilings of rectangles. So you might want to look into that, and he used various techniques, all including electrical networks. Yeah.
Okay, more questions.
Maybe I have a question. So I think you might have mentioned, but I didn't get it. So why does the problem become different if there is a unique minimal tile?
Yeah, so I guess the detail lies in the proof of the problem. I don't remember the details of a proof right now, but somehow so if there is no minimal tile, you get a bunch of you get to solve a system of equations, a system of Diophantine equations, and then that makes everything nicer. But if you have a unique tile, then your system of equations collapses. So you can't just solve it by number theory. You need more than number theory. Yeah.
Okay.
Yeah, is that clear?
Well, I have maybe an idea, but not sure if it's the correct one. But
what's your idea? I would be interested to
so
hear.
no, my question is, do we then have maybe not? So can we have rational side lengths or no? Or is it always rational, or can you also have irrational? Or
Let's see. When you have an MTP tiling, it must. So you mean like if you resize the square so
Yeah.
that the smallest tile has edge length 1,
Mm-hmm.
the side lengths are always integers, yes.
Okay. Okay.
Yeah. You might allow them to be rational, so then you would have a more general case of MTP.
Mm-hmm.
Yeah. So that's a good question. Like, I think if you look at this example back here, here, for example, this might have rational length,
Yeah.
I think. Yeah.
Mm-hmm.
Yeah. Yeah.
Okay, thank you.
Yeah.
Okay. Are there more questions? If not, let's thank Nart again
Yep.
for the talk.
Thank you.